standard Borel space with a measure class,
Yes.
then you take the completed sigma algebra.
Somehow I want you to remember, yes, you do have the completed sigma algebra,
And
but
this is not standard Borel.
what do you mean this is not?
This is not a standard Borel.
No, sorry. Yes, this is not. When I say on the backspace, I want you to remember the sigma algebra also before completing. When I talk about maps between Borel spaces,
Yeah.
I want them to be Borel up to null sets, and not just Lebesgue measure, which is something we never in math Lebesgue measure, right? We might, but it's not. It's a considerably less useful concept than Borel maps defined after measure sigma. So I started a new subject, and I now I spent some time on explaining the basics of the meaning of the concept in space, and so maybe part of the definition. What I want to define here in this paragraph is S on X is ergodic, as per the line definition. If for every A in X, so this should be read Lebesgue measurement, which is S invariant either mu A is 0, or mu is my measure, or mu X minus A. Equivalently, and by the way, again, mu here is a measure, or maybe I want to think about it as a measure class. I care mostly about zeroness of sets. Nullness. Nullity. Okay. Equivalently, I want this is the same as saying that L infinity X S fixed point is just a constant. It's one dimension. Okay. Now given is map O from F to G, and a backspace, and S the backspace, X, an algebraic representation of X, is the following data. And by the way, I guess I failed to write it down properly, but I said it. My map rho is assumed to be a continuous map into the k points over some valid field, and so I have in my background some field with an absolute value. Then whenever I discuss algebra or geometrical concept, I'm assuming they are defined over this field. So the group here is the set of points over the field, and now variety. V, a K action. G on V. So since G act on V, also S act. Also GK act on VK, and S acts on VK as well. So I want an S equivariant. And let me map from X to VK. Just to be clear about it. This will act here, this will act here. I have a row here, and I'm asking for this phi, such that I can move to X. So, let me emphasize. I'm fixing S. I'm fixing this data here. And the representation is the choice of this guy and the choice of this L. So fix S, X, G, or vary V, V. Get a category. Elements or objects. And the bottom of the of X. Morphisms. And Toy diagram. So if I have a map to U and a map to V, so this is maybe VU, VV. A morphism will be so these maps commute with S equivalent. So S acts here, G acts here and there. So a morphism will be compatible G and Y.
Maybe it's a good question for examples of X.
So I will give a theorem first, just to see how things fit nicely. Why is it so fruitful to match somehow, to let algebraic theory and algebraic geometry play one against each other, and then I give some examples.
Should the map be S equivariant also between U and V?
So it is G equivariance, since S acts via the map to G. Oh, and it came up.
So theorem, if X is S-symbolic, then this category is the initial object. Some
some algebraic subgroup H naught inside G. So this means that, let me explain what it means. I'm having some fixed guy, G mod H0. And whenever you have another representation, there is a canonical, unique G map between this closed space and this guy V. So how I put this? So first of all, let me find it with it. Here, this will fall from all this. For every representation, x to v, there exists some x to g mod h, maybe not the canonical h yet, with basically what this observation says is that whenever I map this ergodic space into algebraic variety in a covariant way, basically I'm hitting one orbit, one G orbit. So, so you have X, it is mapped to G, to V, sorry. And now take the map to V mod G. This is the orbit space. The G orbit space of V. Now, this is not an algebraic variety, but it is a nice viewed as an OS space. Think about it as a space with a sigma alpha. And we know that orbits are locally closed. And we know that this is S-ergodic. And this map, of course, this map is G invariant. So this map is S invariant. So you take the measure here, this S-ergodic measure, and you push it here. But here, S acts trivially. S acts via the embedding into G, which is trivial here. So an ergodic measure on nice space with a trivial action must be supported on one point. So
It's still algebraic.
sorry?
When you push them,
Yeah, so, yes, what is the definition for logistic? Always, when I have a map from X to Y, if X is ergodic, I cannot find an invariant, a non-trivial invariant set here, because its pre-image here will be a non-trivial invariant set of measure, which is. So I can find whatever the image here will be 1 point here, and hence in V it will be supported on the pre-image of this 1 point, which is some orbits. And this is the proof that. Okay, so what goes into this observation, which is crucial for us, is the interplay, the tension between these two properties. Ergodicity on one side, on the X, which I'm assuming, and the fact that on my V's, the orbit structure is so nice, which is something that we started to prove. And now, I will prove the theorem. after that, as I promised, we'll give some examples. So I want to provide an initial object. So whenever I have a map to whatever v, I can somehow find a map x to g mod h. Whenever I have a map to v, let's try to sketch how we would go and prove it. Now, of course, if I have a h prime which is bigger than h, I can view g mod h prime as a factor of g mod h. And I can compose this and view this as a morphism between two representations. So somehow when I want to go initial, I'm looking for as small h as I can. If I have, I don't know, h0 which is smaller than h, I have a map from here to here, and I can ask myself, can I lift further here? So the game is to lift as much as I can. So let's formulate this. Consider the collection of all h inside G such that h is paired by subgroup and there exists a representation into G mod h. Of course, by this I'm abbreviating. I'm not writing down explicitly. This is as a variant. So this is to be understood. Okay, so I'm looking at the collection of all possible guys that fits in this picture. And I want to take h as minimal as I can, as small as I can. And I can do this because by the Noetherian property of G, every collection of closed set has a minimal element. This is one of the many definitions of the Noetherian property. There exists h0 which is minimal with respect to inclusion. And of course, with this h0, there exists some phi 0. Goes there. As the notation suggests, I want to claim that this is my initial object. This is a good candidate, because I cannot lift further, somehow, according to this picture. But it is not clear a priori. So this by minimality of this G, of this h0, I cannot lift to whatever that factor through that. But it's still not clear that I can go from G0 to B. Need to show that for every x to v, there exists a map v mod h to v, maybe I, let's call it g mod h0, such that if I compose what is the order I is phi 0, I will get v.
Isn't it clear from this observation?
So it is clear, of course I will use this observation, it is clear that there is some G mod H. But why is H0 smaller than that H?
But you took it as a minimum.
Yeah, okay, there is an ambiguity in the notation minimum. Is a minimal element is not the unique minimal element a priori, right?
Oh.
So, I mean, I'm bound to show that this is the unique minimum. So far, what Noether gave me is that I can find this H0 which there is no other guy below it. I don't know yet that it is smaller than any other value. I'm about to prove it. Oh, and by the way, it's a little delicate. It's not that it will be also a unique minima, because when I look at Gmod H0, yeah, I can take any conjugation. I mean, this space is the same as Gmod every other conjugation of H0 by choice of another base point, and well, I guess the phi 0 that I will be using will have to, if I change coordinate, will have to be different. But this is
But they are isomorphic in the category.
they are isomorphic in the category. Yes, but not. But looking at such a collection, they are not isomorphic. So it's not a big deal. Yes, they are isomorphic in the category by this conjugation. So just H0 will not be a unique minimal. It will be unique minimal after conjugation. Every other H in here will contain one conjugation. So, okay, now I'm showing this. And I'll show it by drawing this diagrams. I will have Gmod H0 here. I have V, and I have X somewhere here, and I have color, green one. I have this guy, phi, and that guy, phi 0. And I will form the product representations. This is something I can do easily. Here's the product of the space, and of course I can take the product of these two maps. This is 3 times this. Now I'll use the observation. I will use this with respect to the product. Where's the observation? Take V to be that product, I will be able to find Gmod H, some H. That I'm getting this, right? This is by the observation. But the observation buys this to me. And of course, this H now, just by the existence of this green map, becomes an element of C. But now, look, I'm having, or composing these two, I'm having this map over here. So these two representations of X are related by this morphism. This is a G map. And this exactly means that, again, up to conjugation, H is smaller than H0. Right? Look at the, take the base point here, which is stabilized by H0, and take a mirror image of it here. The stabilizer there will be something which is a priori smaller, right? But, and of course it will be a conjugate of H. But by minimality, if smaller, or actually if smaller or equal, must be equal. So this must be an isomorphism. And so I do get this map back, just out of the minimality. It's by minimality. F0. And of course I do have this map over here. And now I got myself composing, I'm getting this one. And green. And so this shows that for every V, I'm having a map from this guy to this, which commute with these two terminals. And by the way, I said to begin with that this map is unique. I'll leave it for you to express this. It must be unique by the fact that it must commute with X. I mean, but by commute, take any point, or a generic point to be precise, little x here, take its image here, and its image here. That image here must go to that image here. But since this is a homogeneous space, then by fixing one point, I know well every other point here. Since this is homogeneous and this is a G-map, by fixing one point, I know well every other point wrong. So if there exists another map, it must be the same.
This is because S is a risky density G.
No, I was not using this actually.
But you only know that this map from X to V and G on H not is S is equivariant.
Yes, but just a minute. No. To say that a map here, given these two, given X, now this is not about S at all.
Okay.
Assume you have X, you have these two green maps here and here, and assume maybe you have two maps, both are G maps, and this is G homogeneous. This is enough to conclude that they must be the same. Because, take a point here, I mean, I should be careful about picking a point, right? I should argue with almost every point or something like that. But let me cheat just a bit. Take any point here, take phi of that point here, phi 0 of that point here. This map is alpha, this map is beta, and alpha of that point equals that, and beta of that point equals that. So alpha and beta both agree on one point. So, being G maps in this homogeneous space, they must agree everywhere. So I must give some examples of this construction. Basically, if we omit if we replace this maybe not so familiar notion of ergodicity here by transitivity, and I claim that I'm redefining somehow the concept of the risk closure of a sample. Let me explain. Assume X is S mod T for some T closed homogeneous. So what is the representation then? Maybe it's up here, keep acting here, this is all. Look at maybe X, let's call it X, ET, the base point. What will be the image of this? These must go to some V, which is T fixed point, right? But if this point is fixed by T, or if it is fixed by T, means it is fixed by rho T, then also it is fixed by the closure of rho T, right? The stabilizer of a point is also always algebraic itself. Is risky closed. So the collection, obviously every point which is fixed by the closure of rho T is fixed by rho T. But if a point is fixed by rho T, it is also fixed by the closure of it. So maybe let's see, where are you? let me call it H. H is moreover, for every also if you want maybe I'll rewrite it. So to say that V is H fixed is basically to say that there is a map S mod T to V actually factor. This is GH here goes to GB. What? For any V in V or V in VH, there exists a map G mod H to V. Again, GH goes to GB, and I can
So many arrows.
yeah. Things go from here to there. Okay, so this proves. Oh, obviously. Maybe I'll just let me give you P0. Obviously, I have so I thought the map S goes S from T to G from T goes further to G mod G mod H. So let's call this P0. And this proves that discussion about shows that is the required initial.
For algebraic action,
So far, so here I was avoiding ergodic actions. This is not good.
but the action is algebraic, isn't there some notion of generic stabilizer?
No. Or typically generic stabilizer will be here.
But this this initial object won't be true.
Yes. So somehow, yes. The thing is the following. The phenomena is that in algebraic geometry, you can't be ergodic, basically, unless you have transitive. And then you do have a stabilizer. And of course, for a transitive action, stabilizer is you canonically defined after the conjugation. It's a subgroup. You may view ergodic action as some sort of a generalization of a transitive action when you don't really have a subgroup. Some people call it virtual subgroup. But it doesn't exist as a subgroup. Really, and but so you think of this think of this as an ergodic action, and this is some sort of a shadow of it in the algebraic category. It must be transitive, and the minimal stabilizer that you might get will be this initial object. Maybe I'll there's a terminology here. Terminology. think of X as you think of an algebraic representation as a way to put this thing into an algebraic honest algebraic category, and this is the door. The G mod H0 is the door it must enter the category through. So if your ergodic action was transitive to begin with, this is nothing but taking the recit closure of the stabilizer. So the things become more interesting when we deal with actual ergodic actions. And I want to discuss this, but before this, so now I guess I should shut this door and put this general nonsense aside and discuss the preliminaries of ergodic theory for algebraic groups. So let's put a dot here.
So your law would be just the identity in most cases?
No, I mean in this. Rho. In many cases, the group S will be an actual suburb of G. It will be an inclusion. So this is useful when you study many times arithmetic suburbs, often algebraic groups. So this is the inclusion of an arithmetic suburbs, or representation of an arithmetic suburb of one group into another. So somehow, many times I will have my abstract S, and I would like to compare two algebraic representation of it into different algebraic groups and say that they are related. If the structure here is rich enough. So in the back of my mind, I have this beautiful theorem of Margulis called superrigidity, saying that for some groups, all algebraic representations are, let's say, classifiable, and by this means you can classify them all. And I will explain this. But we will have to develop the setting further. But now, okay, so I expose this very abstract set of definitions and abstract theorem. It says nothing without examples. So now, again, I want to make some examples. So before discussing ergodicity, let's discuss metrics of groups. This is a completely new chapter. Method of groups. On groups and varieties. So let me be very, let's take S2 out. And so it's act on a plane. The plane basically is R2 minus 0. Here's one orbit, and 0. Here's another orbit. This is isomorphic to G mod U when U is 1, 0. Right? So this is the map here is the map to R2 here is GU goes to G of 1, 0. And obviously U is a standard. And maybe before discussing metrics, let me let me draw for you the dynamics of you acting on R2. I guess we have this picture several times already on the board, did we?
Actually had it in the office and in this Sunday.
Okay. So what did you say about?
Prove something.
An extended class property.
Okay. Oh, okay. So so the pictures that I will. So this is very much related. So 0, 1 is fixed by U, and also every other point in here. So So as a field draw here, the other orbits are like that. And also let me take A to be lambda lambda inverse. So let this act on R2. And the orbits look like that. Well, 0 of course, fixed. This axis is one orbit, this axis is one orbit, and here's one orbit, here's another, etc., etc., etc. Just hyperbolas. By the way, draw your attention that the fact that here the orbits are closed. This is always, I did prove this here. This is always the case when you consider a unipotent group acting on the variety. Here, not all orbits are closed. This generic orbit are closed. But these orbits, for example, is not closed. This fixed point is in its closure. But all orbits are locally closed, of course. And now, claim no invariant, no G-invariant metric on R2 or on G mod U. Let me explain this thing. I will not write out to explain it by looking at this. So assume you have on R2 a G-invariant metric. In particular, it is invariant to U and invariant to A, right? I want to show that, I want to explain for you that the distance between every point, every 2 points, will be arbitrarily small. Will be smaller than epsilon for every epsilon. And this for every 2 points. Okay? So let's start by the base point. Here is 0, 1. So let's take the epsilon ball of it. Oh, I guess that there are invariant metrics. The discrete metric is one. Okay? So, continuous with respect to the standard topology. So let's look at the epsilon ball of this point. So it will contain some neighborhood by continuity. It will contain some neighborhood of this point. But now, so it will contain, for example, some point which is not on this on the axis. But if the distance between this red point and this orange point is less than epsilon, same goes for every other point in that orbit. Right? Since this point is fixed by U, so the point, the main orange again, the distance between this x and this y is the same as between the distance between ux and uy. But uy is y. Y is fixed. So this is in the ball again. So the ball actually, if it contains any point, it will contain all this line, this horizontal line here. So actually it will not be a ball, it will be a strip. The epsilon ball will be some sort of a strip, right? Of some width, some delta width above and below the x-axis. Now take any 2 points, I don't know, this and that, and try to compute the distance between this and that. I want to show to you that it is less than 2 epsilon. So instead of looking at this x and this y, let's apply for maybe a huge lambda, lambda being 1 million, let's apply this a. So what does, so it will take you deep into the strip. This number, right? And this will go somewhere here. This would be AX and AY, they will be in the strip. So the distance between AX and AY is the same as the distance between X and Y, but both are in the strip of a diameter less than 2 epsilon. So this is arbitrary as well. Okay? So I explained that, right? Break is good, yes.